Welcome back, detectives. In today's investigation, we're diving into AdaBoost, one of the most popular ensemble learning techniques. Now, before we jump in, I'm assuming you're already familiar with decision trees, as this is crucial for understanding how AdaBoost works. Decision trees are like our single investigators, each working through clues and making their best guesses on their own. However, we know that any investigator, no matter how sharp, can sometimes miss details or make mistakes. That's where AdaBoost comes in. AdaBoost, short for adaptive boosting, is a method that builds a team of weak decision trees investigators that may not be strong on their own but, when combined, can solve cases much more accurately. What makes AdaBoost special is how it adapts over time, learning from the mistakes of earlier trees and giving more focus to data points that are harder to classify. So, as we go through this video, we'll uncover the step-by-step process AdaBoost uses to create this ensemble, how it balances the strengths of multiple trees, and how it adapts with each new round to improve accuracy. By the end, you'll see why AdaBoost is considered a foundational algorithm in the machine learning world. In order to understand the concept, let's take a simple dataset containing information on various factors that may influence product sales. Each row represents a record with the target variable, sales, affected by temperature, weekend status, ad spend, and discount levels. How does it work? Alright, detectives, it's time to get to work. AdaBoost, our mastermind investigator, has just received the case file, which is our dataset, full of clues about sales. Now, before any detective can start solving this mystery, AdaBoost uses a clever technique called bootstrap sampling. Don't worry, I will explain this method in a minute. But here's the catch. Since we're just starting and haven't made any mistakes yet, AdaBoost gives equal weight to all the clues. This means, for the first round, every clue is just as important as the others. Since we have 5 sets of clues, sample weight for each clue equals 1 divided by 5 or 0.2. Now, let's get into how AdaBoost picks the clues in the most intriguing way, like a detective choosing which lead to follow next. AdaBoost doesn't just pick clues randomly, it has a clever method. First, AdaBoost generates a random number between 0 and 1, let's call it x. This number is the key to selecting the next clue for our investigation. But here's the twist, AdaBoost doesn't pick the clue at random. It takes into account the weight of each clue. The clues that have higher weights because they might be more suspicious or important are more likely to be chosen. Here's how it works. AdaBoost checks which row x corresponds to, using the cumulative sum of the sample weights. For example, if x lies between 0 and 0.2, AdaBoost picks the first clue. If x lies between 0.2 and 0.4, it picks the second clue, and so on. The idea here is that clues with higher weights are more likely to be selected, as their importance increases, but all clues have a chance to be selected based on their weight. Suppose AdaBoost chooses x equals 0.61, so it puts this entry in the bootstrap sample dataset. Then it chooses x equals 0.3 randomly and put the subsequent entry in the dataset. In similar fashion, AdaBoost keeps on choosing the values of x till the bootstrap sample dataset equals the length of original dataset. With the sample dataset ready, it is time to call the junior detective. Note: in practice you can use any estimator as the weak learner, but in this simple dataset, I am going with decision tree regressor. After analyzing the given dataset, detective makes a decision tree with depth equals 3. And with this, task of this junior detective is over. AdaBoost brings the original dataset and uses this tree to get the predictions for each row. Let's solve for the first row ourselves. First question decision tree asks is whether discount is less than or equal to 7.99. Looking at out data, discount 8.25 which is more than 7.99. We move to the next level. Now the question asked is whether the temperature is less than or equal to 37.59, which is true in our case, so we move to the next depth accordingly. Now, since there are no more questions to be asked, we predict the value of this data to be 119.35. Similarly, AdaBoost calculates the predictions for the entire dataset with the help of this single tree. In AdaBoost, after making predictions, it is important to calculate the errors to understand how well the model has performed. AdaBoost uses different methods for calculating errors. The absolute error is the difference between the actual value and the predicted value, taken without regard to sign. It is a straightforward metric for understanding how much the prediction deviates from the actual value. The squared error is another method where the difference between the true and predicted value is squared. This method penalizes larger errors more heavily. The exponential loss is used in AdaBoost to calculate the error based on how confident the model is in its predictions. This loss function increases the weight of incorrectly classified points during training. Taking the absolute error for all the rows and doing the math, AdaBoost has the errors made by the first decision tree. After this, AdaBoost normalizes these errors by dividing all the errors by the maximum error, which in our case is 44.12, giving us normalized error. Up till here, the methodology is pretty straightforward. I am reducing the data frame to create more space for the next part of calculations, which is the core of AdaBoost. It is time to calculate how close the decision tree is as a whole and how much importance should be given to this junior detective. For this, AdaBoost starts by calculating the weighted error of the entire tree by using this formula. Since there are only 5 data points, we can calculate the weighted error easily ourselves. First, we multiply weights by normalized error for the entire dataset. Then, we take the sum of these weight errors. We also take the sum of the weights. Note, you must be wondering what is the use of taking the sum of the weights since it will always equals 1. The sum is taken to avoid any rounding error. Also, if this weighted error equals 0, it would mean Junior Detective was able to predict the sales value with no errors and AdaBoost gives most importance. But if the weighted error is greater than 0.5, AdaBoost has a tendency to completely ignore this detective and remove it from the team for the final prediction. Once we have the weighted error, we calculate beta, which represents the relative accuracy of the estimator. If the weighted error is low, beta will be a small value, indicating a strong estimator. If the weighted error is high, beta increases, signaling a weaker estimator. In this case, beta equals 0.2 divided by 1 minus 0.2, which is 0.2 divided by 0.8, thus our beta equals 0.25. Finally, AdaBoost calculates the estimator weight, which determines how much influence this estimator or weak learner will have in the model. This weight is scaled by a learning rate and the logarithm of the reciprocal of beta, which adjusts the weight depending on the accuracy of the estimator. This scaling ensures that weak learners with smaller errors contribute more to the model. Now, it is time for AdaBoost to change the weights of each data point. For the next junior detective, in AdaBoost Regressor, after each iteration, AdaBoost updates the sample weights using a specific formula to ensure that the model focuses on the harder to predict samples in the next round. The formula multiplies the current weights by a factor that depends on beta, which represents the performance of the current weak learner, and the normalized underscore error, which shows how far off the predictions were. Misclassified or poorly predicted samples have their weights increased, meaning the next weak learner will pay more attention to them. On the other hand, correctly predicted samples see their weights reduced, as they are already well handled. This iterative process helps the regressor build a strong model by addressing weaknesses in each step, ultimately producing more accurate predictions by the end of the boosting process. Let's apply this formula in our test case to validate this. For our first data entry, current weights is 0.2. And our first detective was correctly able to predict the sales value. So, AdaBoost must have reduced its weight for next detective. Substituting the values and solving the equation, we calculate what AdaBoost must have done and update the weight for the first entry. Similarly, we can calculate the new weights for the entire dataset. After calculating the new weights for each sample, the next step is to make sure that the sum of all these weights equals 1. This is an important step in the AdaBoost algorithm, as it ensures that the model doesn't become biased towards any particular sample. By normalizing the weights, we maintain a balanced focus on all samples, preventing the model from becoming overly influenced by a few samples. To ensure that the sum of the weights equals 1, we simply divide each individual weight by the sum of all the weights. If the sum of weights wasn't normalized, the updates would distort the importance of the samples over time, leading to poor model performance. Keeping the sum equal to 1 ensures that each sample's weight is proportional, allowing the algorithm to progressively improve without favoring any one sample too much. It is also worth noting that the higher the error of a sample, the more weight is assigned to it. This ensures that the next weak learner, or detective, pays extra attention to these problematic samples. In AdaBoost, this means that misclassified samples are given more weight, which forces the algorithm to focus on correcting those errors in the next iteration. Essentially, AdaBoost gives more weight to these samples when generating the bootstrap data sample for the next weak learner. This helps the model improve by emphasizing the areas where it previously made mistakes, leading to a stronger, more accurate overall model. The weights in our original dataset are updated based on the new weights calculated after each iteration. After the new weights are computed, the algorithm assigns them to the corresponding samples in the dataset. This adjustment is done after every iteration, allowing AdaBoost to continually improve by focusing on the hard-to-predict samples, ensuring a more accurate model in the end. Alright, let's recap everything so far by building another tree in this iteration. We now have updated weights for all the samples in our dataset. These weights guide us in generating the new bootstrap sample for our next tree, or as we call it, the next detective. Here's how it works. If the random number is less than 0.1 to 5, AdaBoost selects the first row. If it's between 0.1 to 5 and 0.5, it selects the second row. If the number falls between 0.5 and 0.75, it picks the third row. If the number is between 0.75 and 0.875, it selects the fourth row. Finally, if it's between 0.875 and 1, it selects the last row. Notice how these ranges are based on the weights we just calculated. Rows with higher weights have a larger range, increasing their chances of being selected multiple times in the bootstrap sample. For example, if the third row has a significantly higher weight, it will likely appear more often in the new dataset. This increased chance ensures that the next detective, or weak learner, focuses more on this entry, addressing its error better and improving the model's overall performance. Each iteration builds on the mistakes of the last, and this sampling process plays a key role in making AdaBoost such a powerful algorithm. Let's understand this new dataset prepared by AdaBoost by randomly selecting 5 values of x. Based on the updated weights, there are 2 important things to note here. A sample with a higher weight has appeared twice out of the 5 selected entries. This makes sense because higher weights increase the likelihood of a sample being chosen multiple times. This ensures the next detective focuses more on correcting the mistakes associated with that sample. There is another entry that has appeared more than once, but this is purely due to the randomness of the sampling process, not because of its weight. This happens occasionally since the dataset is created using a random method. It's also worth noting that, although rare, it is possible for a high-weighted sample to not appear at all in the new dataset. However, the probability of this happening is very low because its high weight makes it far more likely to be selected. This random sampling with weighted probabilities is what makes AdaBoost so adaptive. It ensures the algorithm gives more focus to difficult samples while maintaining the randomness needed to prevent overfitting or bias in the selection process. Once the new sample dataset is prepared, the junior detective, our next decision tree, steps in to do its job. This tree is trained, or fitted, on the new sample dataset, learning patterns from it. After training, it evaluates the original dataset by making predictions for each sample. These predictions are then passed back to AdaBoost, which uses them to calculate the errors for this round. The goal is to identify where the junior detective succeeded and where it struggled. These errors help AdaBoost decide how much weight to give this detective in the overall model and how to adjust the sample weights for the next iteration. So, in essence, the junior detective focuses on the sample dataset it's given, learns from it, and sends its predictions back to AdaBoost to continue the improvement process. Then AdaBoost divides each error by the maximum error observed in this round. Why is this step necessary? Dividing by the maximum error ensures that all errors are scaled down to a range between 0 and 1. This normalization prevents excessively high errors from dominating the calculations and ensures that the weight adjustments remain proportional. Without this scaling, a single sample with an unusually large error could skew the entire process, making the model less balanced and effective. Once the errors are normalized, AdaBoost calculates the weighted error for the current iteration. The weighted error tells AdaBoost how well the junior detective weak learner performed overall, considering the importance of each sample. A lower weighted error indicates that the weak learner has done a good job, while a higher weighted error suggests there's room for improvement. AdaBoost uses this value to decide how much weight to assign to this weak learner in the combined model. Next, AdaBoost calculates beta, which measures how much influence this weak learner, or junior detective, will have in the overall model. A higher beta indicates that the weak learner made a lot of errors, meaning it should contribute less to the final model. Conversely, a lower beta suggests good performance, giving this weak learner more influence. Finally, AdaBoost calculates how much say, or influence, this junior detective should have in the final model. After determining the influence of the current weak learner, AdaBoost updates the sample weights to prepare for the next detective, or weak learner, in line. Also, keep in mind that once the weights are updated, AdaBoost normalizes them. How AdaBoost predicts. Let's break down how AdaBoost works when predicting the sales for the first data point using the trained 10 junior detectives. Each junior detective predicts the target. After that, the predictions from the different estimators are sorted in increasing order. This is done so that AdaBoost can later calculate the cumulative sum of the weights based on the sorted predictions. After sorting the predictions, AdaBoost calculates the cumulative sum of the estimator weights. This step helps in determining which weak learners have more influence in making the final prediction. AdaBoost is interested in the median prediction. The cumulative sum of the estimator weights is compared against 50% of the total weight. This helps us identify the estimators whose predictions contribute most to the final outcome. The final prediction is the prediction of the estimator that corresponds to the median cumulative weight. In other words, the prediction is made by the weak learner whose cumulative weight reaches or exceeds 50% of the total weight first. Common pitfalls and misconceptions. Sensitivity to noise. AdaBoost Regressor may overemphasize outliers, assigning them higher weights and leading to skewed predictions. Choice of base regressor. The performance of AdaBoost Regressor depends significantly on the base model. Overly complex regressors can lead to instability. Overfitting on small datasets. On small datasets, the iterative nature of AdaBoost can cause overfitting, where AdaBoost Regressor shines and should be used. Improving weak models. Ideal for boosting simple regressors like decision trees to achieve better predictive performance. Moderate noise. Works well in datasets with moderate noise levels, where it can iteratively focus on hard-to-predict samples without overfitting. Nonlinear relationships. Effective in capturing nonlinear patterns in the data by iteratively refining weak learners. Thank you so much for spending your valuable time learning about AdaBoost Regressor with me. I hope the concepts are now clear, but sometimes they need just a little more time to settle in. So, if possible, give this video another watch. It'll help reinforce the ideas and make sure they stick in your brain. Your support means the world to me, and I look forward to exploring more algorithms with you in future videos. See you soon, detectives.